Hello, everybody. My name is Manny, and today I'll talk about fixing small files performance issues in big data with DataFlint, which is an open source library I'm the author of. And please, if you have any questions, feel free to interrupt me on time. So, little about me. My name is Manny. Served in the 81 unit. I worked at Ex-Ziprecruiter as a data engineer, then Granulate as a weird combination of security research in big data to use cyber security tools to improve performance of big data engine in the big data world. Interest in data engineering, backend, front-end, ML, infra. Very passionate about data engineering, and currently working on DataFlint full-time. So let's start talking about big data. So the underlying most basic layer of big data is the storage. So we start with a database like Oracle database, MySQL, SQL Server is the initial solution. There is a big server with a bunch of disks and compute and like does our queries like a select and inserts and so on. And at some part, like the big data problem, this can have 1 terabyte, 2 terabytes, 4 terabytes, but at some point we need more data than one disk can have. Also, in traditional databases, even data warehouses, the storage and the computer are coupled. So if I need more disk, I also need a stronger and much more expensive machine. And at some point, like this solution just doesn't work at scale. So we go to the solution of the storage in big data, which is initially was HDFS, which is a Hadoop file system. But today we all know it as S3. S3 is basically HDFS compatible, it's basically HDFS. And the idea is a distributed file system, which feels like a Linux file system, but underlying it, it's a blob storage, meaning we save and retrieve really big files, ideally hundreds of megabytes to 1 gigabyte. This is like the sweet spot of this kind of compute. And we also, we can't edit a file. We can also only override the file completely or get it. But with this disadvantages of this trade-off, we get a very, very cheap solution that is also can save petabytes of data. And we also can retrieve all the data at once. When traditional database we have IOPS, we can only get a certain number of rows each second. And if you want to get all the database, it's really hard. Here you can fetch all the database and get great performance. This is the underlying base of big data. Of course, from here we have a bunch of problems. Like if we have a user table with or a bunch of user data, we need to delete one user. Like because of GDPR or anything, how we do that, and a lot of big data and big data engines problem starts. So this is the underlying part of big data, which is the storage. So a very simple example of how storage in big data looks like. We have like, here it's my local machine, but the idea is this is how Linux file system looks like. We have a bunch of folders, which we call partitions. In this folder, only data which is associated with a certain key or set of keys is inserted. Here, it's usually 99% of the time, it's a date. Like we have a folder for each date we want to read, and here it's like a sales, store sales information. So we have the date the item was sold, and under that we have the files, which again should be really big files. Otherwise, we'll have performance problems in both the storage. Yeah.
Yeah, well, names that you are happy with the names as well as 1 minute.
The names of what exactly?
My apologies, sorry.
Okay, no problem. Anyway, we have like the fields, which are the folder name, and under that we have the actual files, actual data, which is usually in some big data formats. CSV or JSON are really have poor performance, so we usually use the Parquet is the most popular. We have OC and we have Avro, and formats that are most have like better performance for big data, for saving a lot of data in one file. And again, they should be really big. This is if they are small, there will be performance problems. Awesome. So we talked about the storage part. Let's talk about the compute part. So we have the data. We have like terabytes or petabytes of data stored in an efficient way. How we query them? So we use a big data engines, which is a distributed engine. In the example, we use Apache Spark. This is the most popular engine. In big data, the compute is totally separate from storage in almost all cases. And the idea is that we get a bunch of machines, can be 1, can be 10, can be 1,000. We have one machine called the driver, which is the one that takes a query, parse it, plan it, and then get a query of task. Task is one unit of work, and then it like distributes the work to workers, which are called executors in Spark context, and each executor takes few tasks as a number of CPUs. And in our case, let's say we have 2,000 files to read, and we need to filter them. Then each task will take maybe one file, maybe a few files, and it will filter it, and after that, it'll go to the next thing. So again, we have like a distributed engine. We have task queue. We have each executor taking tasks, and task is a unit of compute. You need to take like read some files, take a unit of partition of data and do some computation, or like output it, save it to somewhere else. So this is the compute part and totally separate from the storage. And another thing worth remembering, again, I'm hammering the point, task is supposed to be big. If like task is like to only process one or only few rows, this is really inefficient because we have like a mechanism for taking a bunch of tasks and scheduling them and get the results and so on. So the engine also expects the files that we are loading and saving to be big, because the task will be bigger, and then like the job or the distributional computation will be distributed evenly and efficiently. Awesome. Last concept we'll talk about is shuffling. What is shuffling? So let's say we load some data, but then we like by date, but we need to do the computation. Let's say group by or join by the country name of the sold item. So we don't have an efficient algorithm for that to do like in a distributed environment. So the most efficient thing you can do is just reshuffle the data. The executor can talk with each other and like swap information. So each executor will have all the relevant information for a country, and then we can take this data and like do a group by. We can do a join, like take two pieces of tables with the same country and join them together, and so on and so on. So the executors can shuffle, be imported in the example. Okay, cool. I want to do like a hands-on example on everything we said so far. So here I have a 25 lines of PySpark, which is a Python variation of Spark. If you don't know Spark, you don't know syntax, don't worry, I'll like going through it. It will be like pseudocode. So the idea is that this line is opening the cluster, opening the sessions. These two lines are the magic lines that install DataFlint. Again, libraries that give you better performance observability to clusters. In this line, we load the sales file location, which is the same like as I showed you in the slide that showing how data looks like in a big data environment. Then we filter it by the quantity. So take every sales rows that sold more than one time. And finally, we write the data to a temp directory partitioned by the quantity. So we'll have a partition, a folder in the file system for every quantity. So all the data that sold two items in one folder and so on. So this is a very basic ETL. It's the most basic form of big data query. We take data, we filter or do something very simple with it and save it somewhere else. Awesome. So from a code perspective, like code review and so, this code is totally fine. And let's run it to see what happened. So Spark has something called Spark UI, which is a UI that can show us a little about the internals of what the job does. So we need to refresh it every time. but we see it, we have 58 tasks that are waiting to be executed. And we have a tab called SQL, which we can see our query like plan, just like an explain in traditional database. You can see we are scanning a parquet and we filter and we save, but it's pretty hard to read. As you see, like it's a bunch of data. And it's not really clear what is currently going on. So we have this DataFlint button. Once we install DataFlint, we press it, and we can see more clearly what is currently running. So you can see we are reading parquet data. We can see the rows running. We can see we filter by the quantity, and we save partition for a folder. You can see also in real time we have like an alert icon here that we are reading small files, that our average file size is 55 kilobytes, which again, we talked about the best practice for a lot of reasons is to have these files in the hundreds of megabytes in size. This caused a few interesting performance problems as a result. So go to the summary page, shows the result ran. We see like this query ran for 1 minute on my machine. We'll open it. We can see the query again. We read the parquet, we filter, and we write. Now, when the query ended, we also have an alert for writing data. So you can see somehow the data that we wrote is even smaller in files. So each file is now on average 40 kilobytes. And that for each partition, we wrote 99 partitions, and somehow we wrote to them 6,000 files. How did that happen? So let's do, again, a tree operation on this folder. You can see, for some reason, for each quantity, like quantity equal 99, we have a lot of files. Okay, what happened? So this is a quirk of big data engines that like we have a bunch of files. We each task like 58 task talk few files, read them, filter the data, and then it need to save the data somewhere. So each partition, like in Spark internal, have like a data on quantity equal 2, quantity equal 3, and so on, and need to save it to the location. So what the task will do is take all the data that's relevant for quantity number 2 and save it to the folder of quantity number 2. Then take the quantity number 3 and save it to number 3, and so on and so on. And each task will do the same. So we'll have, like, if the data is distributed, so each task will have all the data of each quantity, because this is how it worked. Then we'll have 58 files of each in each partition, when ideally we can have only one, right? Because we have all the data, we just rewrote the table. So like the big data engine assumes that it will be like, if we take the data and just save it, it will be the most efficient. Because again, we read the data, we filter. Now we need to do something with it. Like the data need to go somewhere. So let's save it just. So DataFlint also have like recommendation section. So in the alerts, we have like suggesting what to do. It's suggesting to do something called the repartition by the keys that we are saving, which in this case is the quantity. So what is a repartition? In repartition, we'll ask Spark to do a shuffle based on the quantity. So Spark will shuffle after the filter. Spark will, the execute will talk with each other, and they will get to a situation where each quantity will be in one partition, in one place in Spark, and in one executor. And then this executor can just write one big file to the partition, and then we have the maximum file size or file location that we can have in this write. So if we have like one task with all the quantity equal to data, we write one file, same quantity equal 3, and so on and so on. So it's the idea of shuffling and how it connects here to write bigger files. So let's implement that solution. In Spark, all we need to say for this magic to happen is .repartition, then the column we want to repartition with. And let's run it again. Just a second. We need to also close the folders session. let me remind you that in the last query, it took 1 minute to do this computation. Take the 2,000 files, filter them, and save 6,000 files. And now it took only 7 seconds, which is a huge increase in performance. So if we enter the query, now we can see that we still read small files, but now we write 99 files for 99 partitions. So we can move to advanced mode in like DataFlint viewer to see a little more of the internal of the query. So we can see like what Spark doing like with the shuffling behind the scene. So first thing Spark doing is something called repartition by hash. Each row we take the hash of the quantity, and then we decide which partition it belongs to and like to which executor, which task it should get. Spark by default always partition data to 200 partition because it doesn't know if there is 100 type of quantities, like what is the cardinality? It might be 1,000, 100,000, so on. So usually use 200, and Spark already optimize it afterward. But it's something worth keeping in mind, all the partition sizes and how many partition we have. And after the shuffle, this is a very common performance problem in Spark or in other big data engines. After that, after the repartition, Spark notices that, okay, each partition is really small, so let's coalesce them, that take like a bunch of partition making one, which is, in this case, he decided for 4 partition. Then Spark decided to sort the data because it improved performance. If data will be sorted, and if we'll query by the data, it can do a binary search. And finally, we save the data. So what's interesting here is that you can see the percentage of like what took in the query the longest, and you can see that the sort takes a lot of time. So one of the reasons in the query before the fix, it took so much time, because if you need to sort 6,000 partitions or 6,000 files that you save, and the like sorting algorithm is n log n, if you do it on 4 partitions, it's much better in performance because it's for n log n and not 6,000 n log n. So the compute here is much faster in this case. So this is another performance problem of like if you try to write small files, the sort takes longer. So this is an example of like using DataFlint to fix small file problem, but there are like more like common pitfalls, and DataFlint know to suggest more stuff. And if you're using Apache Spark, I encourage you to look it up. So it seems like this problem is like why it doesn't automate? Why doesn't Spark or other engines like just when you see that you try to save by a partition, they should just repartition before it? So this is not a very trivial decision. The reason is because there is a trade-off that in order to write this bigger file, we need to do a shuffle. And shuffle can be inefficient. So if we have 10 terabytes we try to save, and we want to now shuffle 10 terabytes across a network, it could take a long time. We might need to buffer the data in files during the process, and so on. Sometimes even you give it 200, 300, 400 machines, like doing a huge shuffle, it just won't end. It's like n squared algorithm and can be problematic. And in these cases, it might be better just to save the data as is. And after that, or if we like save the data incrementally, like each hour, and each hour we have small files, we can do a process called the compaction. The compaction is a periodic process, like every hour, every day, every week, every month, that we run, that looks on the table, see like in each partition how many files there is. If there like a lot of small files, it will delete them and will create a new bigger files. So this is how big data works with like on just a regular old Parquet table. There are now on the market like a open data table format called that like adds a bunch of quality of life stuff. The most popular one are Apache Iceberg and Delta Lake, and both of them have like features to do for you optimize write, or like to do this shuffle and save the data efficiently. But in both of these solutions, you still need to monitor, you still need to see like the trade-off, and usually like you need to turn on the setting or like define something on your table. In some cases, this feature won't be turned on. So this is still something that really important to know and about the behavior of big data engines. Questions?
This recommendation that DataFlint given us to repartition I think it can give me one of the other trade-offs can be skew.
Yes.
So can DataFlint tell me not only what to repartition, but to how much partition to do, like 5, 10, whatever?
Yes, if your table is okay, let's split it to two cases. In this case, we saw a table which is have a partition key. So it doesn't matter how you partition in Spark. If you have like a partition of like country like the US and Liechtenstein or some other like small country, and you save the data, because in one place it will be small file, in one big a lot of file. There is no way to repartition the data like because it's physical, because you try to save physical stuff. So there is no magic solution for that. If you save unpartitioned table, so yes, DataFlint will recommend you to how many pieces, like to do a repartition by like round robin, and tell you how many partition you should like split it. So if you have like 1 gigabyte of unpartitioned data, it will say, oh, split it to 8 parts, you'll have like 128 megabytes file size. And Delta Lake and Iceberg doing something similar, like you tell it like in the config, like what is your desired file size. It usually by default 128 megabytes, and it knows like to split the data for you.
Yes, one of the problems that we got in Delta, that the AQE that's supposed to do it, or some other mechanism, in some cases don't do it. So we're trying to figure
this
out
is absolutely right. This is a known problem also with Apache Iceberg. I'm actually writing an article in Medium about it. By the way, like you'll get the presentation, the end of the presentation, there is resources where I go into more details about the problems that I talked. So yeah, the AQE, the optimizer, that took like the 200 partition, made it into 4. It could have like, it has decision rules, and these decision rules might not optimal for saving. So it might be useful to optimize it. Like there are a bunch of documentation in Apache Iceberg and other places how to do that. But yeah, I'm working on an article exactly about that. So this is a really great point.
Great, want to hear it. And I have another small question, not about the small files, but about the big files. If I have like 2 giga files, more than 1 giga, and more than one recommended, do DataFlint tell me if it's too big or? Yeah,
I have also this recommendation. So another classic performance problem, let's say I'm trying to write a table, and in a partition, I have like a partition of 5 gigabytes files. So I don't want to save a huge file like 5 gigabytes because it's also inefficient. Like the sweet spot of performance, like the best practice is up to 1 gigabyte, usually in the 125 megabyte. There are like charts of like recommended size based on the size of the table. And another problem that you might have one task that try to save all the 5 gigabyte. So it might split it to smaller files, but it will do it sequentially. And what you want is to split it to different tasks. So yeah, that you also know to say to, oh yeah, like use this file that you save too big, and you need to do something about it. Like you need to split it to smaller tasks.
Great, thank you.
More questions?
I saw somewhere the jobs were colored, like one was in red and one was in green, and the same thing applied to the tasks. What could those colors represent? Is there what makes them different by putting that red color and green color? Then also another thing, I don't know if
it's like a heat map. Like it's a heat map. Like when the percentage is high, like this is a hot part of your code, like the sort, it's red, and when it's like not important, it's green. So when you look at a query, like big data query, like you load data and then you do computation, then you save. With like traditional Spark UI, traditional engines, you don't know what is a hotspot. Like why the query is slow? Is because of the compute, because of save, because of the load. So DataFlint, like you have like a heat map, and this is the meaning of the colors.
All right, thank you. Just another question. It's my first time here, and I'm glad to be here. I want to ask whether I would have access to the recording Because I don't know how you share the resources.
We are recording this session and we are going to upload it to our website. We are going to send a link with the slides and the video to everyone that RSVP'd the event. So no problem, we are going to have it.
Awesome. If you want to contact me about any question or anything, you can contact me at LinkedIn, Manny Shmueli. You can also, there is a Slack community for DataFlint. You can also find me there. Yeah, thank you.
Thank you very much, Manny. It was very interesting.
Thank you.
Thank you guys for coming. See you at the next meetup.